This is Lab 5, Physics, Pendulum Motion. Our task was from a simple pendulum to capture and extract the data, calculated the period from the motion, plot in the graph window the energy changes that we would compute, and compare in the display window the predicted motion and the observed motion of the pendulum. The principles we used were the momentum principle and the energy principle. This is the tracker program. We had a simple 4 centimeter pendulum bob, 1 meter length on the swing. Initially, we bumped into some problems in that the bob was plumb and it was level, but the camera was not. And this led to some very funny looking data. What we arrived at was that the right side was swinging higher than the left. So we determined that the camera was out of kilter. Made some adjustments, and this is why you have pendulum clocks. Very uniform motion in the X direction, going from one peak to another. We measured the period very consistently, you can see here. Came up with a total period of 2.01667. That's for the pendulum to swing from the right all the way through to the left and then back. A little bit of jitter in the Y measurements. It was a very small measurement on the order of a couple centimeters. Hard to place that with the tracker program. We had to calculate the X and Y velocities. As the bob swings through the origin, you have maximum kinetic energy. So here's the origin, maximum kinetic energy. Maximum distance from the bob here at these 2 points. So kinetic energy here, potential down below. We calculated the period of the pendulum. We came up with 2.016 seconds versus 2.007. So we plugged our value back in, and it determined that our length was 101 centimeters versus 100 centimeters. We would arrive at a value of G using that length of 9.77 meters per second squared versus a book value of 9.8 meters per second squared. With the energy principle, it's the total energy equals the kinetic energy plus the potential energy will be zero when there's no energy in the system from the surroundings and no external forces acting on the system. Then the energy is conserved. We confirm this, but in actual fact, there is a little bit of friction of the string where it attaches to the pendulum point, the pendulum pivot. So here we have a plot of the kinetic energy in red, the kinetic in blue, the potential in red. You can see when the kinetic energy is peaking, the potential energy is at a minimum. A little bit of jitter. These are from the Y measurements and also the velocity calculations, but otherwise fairly good agreement of the energy principle. These are the calculation whoops. This calculates the velocities which are needed for the kinetic energy. The potential energy is just a simple mass times the height times the value of G. These are the calculations for the FNet changes. We obviously had some errors here. You'll see from our Python results that they just do not match up. This just updates the position of the pendulum bob as it swings through each loop with the iterations, and this is the kinetic energy 1/2 mass times the velocity squared, and the potential energy is just the mass of the ball times G times the height that it was swinging. These are the first Python results. We can see that we did have some oscillatory motion, but it doesn't really match what we were hoping to see of it swinging from right to left, varying by a couple centimeters. Second Python results. We looked at the arrows for the FNet, F perpendicular and F parallel. Also some disagreement from the previous results. Finally, the third Python results. See here when we run this program, this is a different loop. We do have some oscillatory motion, very minimum. We would have to go back and take a look at the coding in that, unfortunately. We did have a good agreement with kinetic and the potential energies. We did calculate the period, and it was in fairly good agreement, but the Python program did not match up. Thank you.